Section 11. Continuing to talk about inference. We've talked about confidence intervals. Now we want to talk about hypothesis testing or significance testing. This will be our first go at this, but the following sections will be very similar. It takes people a while to wrap their minds around the idea of hypothesis testing. But the good news is, as I said at the end of the last video, once you have, it's pretty much the same every time you do it. The formulas change, but the basic idea remains very simple. So if confidence intervals are the idea that the parameter is probably close to the statistic, that the population fact is probably close to the thing you have, and again, we talked about there's no probably about the population fact, strictly speaking. But nevertheless, if confidence intervals are the idea that the parameter is probably close to the statistic, then what hypothesis testing does is it turns that statement inside out. We say the same thing another way. It is unlikely that the parameter and the statistic are far apart. Therefore, if what you think is the parameter and what is the statistic, if what you think is the parameter and what happens to be the statistic are far apart, then you might want to rethink what the parameter is, right? So, for instance, if you have a coin that you think is fair, and you flip it 100 times and you get all heads, then what you think is going on with the coin is at odds with the reality of what just happened when you flipped it several times. So, because it would be very unlikely for a fair coin to do such a thing, it's no longer plausible that it's a fair coin. So the basic logic of hypothesis testing is simple enough. You have a theory as to what's going on in the population. If the sample makes it hard to believe, don't. Until then, it's still plausible. Let me say that again because I think people make hypothesis testing way too complicated. You have a theory as to what's going on in the population. If the sample makes it hard to believe, don't. Until then, your theory is still plausible. So as you see, this is all going to be about benefit of the doubt. So that's the basic idea of hypothesis testing. The backwardness of inference, of doing probability backwards, it always confuses people because, again, whenever you're talking about this neck of the course, making conclusions about the population from what we happen to have just gotten, which was random. Well, randomness in the past is always hard to think about, right? So it's always going to be a bit cumbersome to think about properly. For instance, with confidence intervals, we say that the parameter is probably close to the statistic. But it would be more accurate to say that the statistic probably was going to be close to what the parameter is. Therefore, we're confident that the parameter is close to what the statistic happens to be. So you have to be very careful about how you say things. It may seem like technicalities, but it's not. It's a matter of thinking about things properly. With confidence intervals, this is no big deal because you can just compute a confidence interval. And as far as students are concerned, thinking about it properly is kind of optional, right? It's nice if you understand confidence intervals, but the bottom line is you can still compute one whether you understand them or not. So that's a little cynical of me, but from a practical perspective, people generally like confidence intervals because they're basically a matter of just computing one. The only thing that comes up with confidence intervals is the various ways you can ask the question and the various ways you can state the answer. Find a 95% confidence interval. We are 95% confident that whatever is between this and this. Provided our sample is among the most typical 95% we could have gotten, the whatever is between what and what. Unless our sample is among the 5% most extreme, most unusual, the whatever is between what and what, and so forth and so on. The different ways you can ask for a confidence interval, and then the different ways you can report your answer, right? Parameter plus or minus, statistic plus or minus margin of error, or actually subtract it, actually add it, low end, high end. So the only thing that's confusing about confidence intervals is the various ways you can ask for one or talk about them, and a couple of different ways you can mathematically leave your answers. But actually computing them is just a matter of filling blanks, right? However, with hypothesis testing, it goes a little deeper. The idea of thinking about things properly is going to be essential to the process. It's important to understand in the sections that follow, at least the immediate sections, section 11 and section 13, that the problems we do, the actual mathematical problems, are the exact same things we were doing in sections 8 and 9. All we're doing is putting a little logic around them. The new bits, the prologue of the problem, the epilogue of the problem, are entirely logical. They are not anything to do with math or computation. The math or computation, as I said several times, is all old stuff at this point. Now, in a sense, this is a matter of perspective. If we take a Section 8 type problem, I think it was, where am I looking? Here it is, the ESP problem. In a test for ESP, the examiner looks at cards that are hidden from the subject. Each card contains one of 4 objects. The experimenter looks at each of 200 cards in turn, and the subject guesses the name of the card. So, obviously you've got a 1/4 chance of getting the card right. So at a wild guess, if you do a lot of cards, you'll probably get about a quarter of them right? So B is the more interesting one here because it doesn't involve counts and so forth. If the experiment revolves a repetition of 400 cards, find the probability of correctly guessing at least 60%. Well, you run the numbers. You can check out the answer key. I'm pretty sure it was off the end of the chart. If you have a 1/4 chance of getting the card right, then the probability of getting at least 60% of 400 cards right is, well, somewhere between slim and none, right? Almost certainly off the end of the normal chart. So if it is true that you are guessing at the cards, if it is true that you have a 1/4 chance of getting each card right, then the probability of getting at least 60% of 400 cards right is slim in the extreme, right? 0.0000 something, very small. So to turn it into a hypothesis test question, it's sort of implied in the question here, right? This person is guessing at the cards. They just got 60% of 400 cards right. What can we conclude from that? Well, we can conclude one of two things. The probability of it being so intensely small, and let me speak on that for a moment. Remember, when you're talking about continuous distributions, and this is all being done by normal curves, remember, the probability of exactly anything is small. That's neither here nor there, The probability of getting exactly 100 cards right is probably not that big, but it's bigger than any of the other individual possibilities, right? That's not what I'm talking about. You wouldn't be surprised if you got 100 cards right. You wouldn't be surprised if you got 95 cards right, about a quarter of 400, I mean. But because this is so far from a quarter, this is so far from the logical thing you would expect to get, that's what makes it suspicious, right? So individual possibilities are always negligible in large samples. That's neither here nor there. That's unavoidable. But we're talking territory. So the key word there is the at least. If you do that problem as a Section 8 problem, then you see that the tail in question, our p hat, is bouncing around 0.25. And it's a very tall, thin bell around 0.25. So 0.6 is very far away, and consequently the tail to the right of 0.6, at least 0.6, is incredibly small, right? It's about territory. It's never about exactly anything in these problems. The point is the at least 60% territory is so small. It is so unlikely that if you're guessing, you will get at least 60% of the cards right, that you're forced to one of two conclusions. well, the probability being 0.0000 something, either this person who just got at least 60% of the cards right is either the luckiest person on earth, or else maybe you want to reconsider the idea that they're guessing, right? So that's what hypothesis testing is about. At the end of the day, either one could be the case. Now, we've talked about this in the past, and we'll talk about it much more when we talk about correlation and linear regression. But, sometimes weird things do happen. It's just unavoidable. Sometimes cosmically unusual things just happen. I probably gave you the John Adams story. I probably gave you the Edwin Booth story. And if you're going looking for unlikely things, then sooner or later you're going to find them. As George Carlin said, somewhere in the world is the worst doctor, and someone has an appointment to see him tomorrow. So on the other hand, if you happen to have the worst doctor, that would be a little unusual, right? So it's about context. It always is with probability. So at the end of the day, either one could be correct. He could be just very, 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 very lucky. But if you're not willing to go there, then you are forced to the other conclusion, that you are mistaken that he has a 1/4 chance of getting the cards right. Now, what you don't want to do is leap to conclusions, right? This is an ESP test. There is a gap the size of the Grand Canyon between he is guessing at the cards and he has supernatural telepathy, right? So you do want to be very careful about your conclusions. There's a lot of middle ground between guessing at the cards and has ESP. The movie Ghostbusters comes to mind. But, he could be seeing the reflection in the glass behind the person. The person who's showing him the cards could have some kind of unconscious tell. He could just be very good at reading people. There could be some kind of scam going on that we can't even conceive of. Alternately, the whole thing could be a massive cheat because the people who are running the ESP test are trying to keep their funding. Who knows? Anything is possible. You do want to be very careful about the conclusions you leap to. But if the theory that he's guessing at the cards leads you to the conclusion that what you just saw was very, very, very unlikely, then maybe you want to reconsider the theory that he's guessing at the cards. Nothing more. Again, in life you always want to be careful of being boxed in by two choices. Whenever somebody gives you two choices and they're both bad, your best bet is to pick a third one, right? You never want to let people frame the question in ridiculous terms for you. Does he have ESP or is he guessing at the cards? Well, those in fact are not the only two options, so you want to be a little careful about the conclusions you draw. But either he's the luckiest person on earth or he's not guessing. So the idea of hypothesis testing was implied even in these problems back here, but now we want to look at it from the ground up. And this is Section 11, hypothesis testing, specifically for proportions. Like I said, sections 10 and 11 have to do with the PP hat scenario, proportion of yeses, that kind of thing. And then sections 12 and 13 will have to do with the average of numbers situation, but it'll be the same ideas. For instance, section 12 will revisit confidence intervals, but for means. So we toggle back and forth. Confidence intervals for proportions, hypothesis testing for proportions, confidence intervals for means, hypothesis testing for means. After that, we're doing hypothesis tests comparing proportions, hypothesis tests comparing means. It's the same stuff over and over again, so you want to be a little bit careful about it. But for now, we're just tackling the concept of hypothesis testing because it's our first time doing it. So we want to focus a little bit more on the logic of it than we'll necessarily do when we revisit it. But on the other hand, bear in mind, if you don't take all this in the first time we talk about it, number one, that's to be expected. And number two, we are going to be doing hypothesis testing in several more sections, 13, 14, 15, 18, ones that follow. And you eventually get the basic idea of hypothesis testing in self-defense because it's the only major obstacle in this part of the course. And once it clicks, it kind of clicks. And then it's all just variations on a theme. But this is our first go at hypothesis testing, and it happens to be for proportions. So here goes. So section 10, hypothesis or significance testing for proportions. So Count Buffon, properly pronounced, Count Buffon, Georges Louis Leclerc Comte, or however you pronounce that, de Buffon, 1707 to 1788, tosses a coin 40 times and gets 20 heads. As for the "it is I, Leclerc" joke, you are probably not going to get that unless you are a fan of the old series Allo Allo, where the character basically, whenever he wanted to disguise himself, would put on a pair of glasses, and then when he wanted to be recognized, he would pull up the glasses and say, "It is I, Leclerc." So, regardless, here's where we are. So Count Buffon, being either very bored or very rich, decided to flip a coin 40 times. One story was that he was in prison at the time. Another story was that he paid an orphan boy to do it. But the bottom line is he flipped a coin 40 times, and he got 2048 heads, or the 18th century French equivalent thereof. So he flipped a coin 40 times and got 2048 heads. So the question, broadly defined, is this unusual? Is it unusual to flip a coin 40 times and get 2048 heads? Well, let's be a little bit more specific. Would it be unusual for a fair coin to do such a thing? Let's think about that for a second before we run the numbers. Now, if he flipped the coin 40 times and got something very, very far from half heads, say 3,500 heads, then you'd be a little suspicious that the coin was fair, right? It would just be too unusual for a fair coin flipped 4,000 times to give you 3,500 heads. And you'd probably say that it's not a fair coin. On the other hand, if you flipped it 40 times and got 4037, let's see, 2020, so let's say if you flipped it 40 times and got 2017 heads, about half, then you'd say that's perfectly reasonable for a fair coin to do that, right? Bear in mind, when you have a large sample, like I said, being exactly anything is going to be unlikely. If you're thinking of this as bar, 4041 bars, like we did in previous sections, then, the 2020 bar is presumably the tallest, but it is also incredibly thin, right? So 2020 is not so much the most likely individual possibility, it is, as it is the least unlikely possibility, right? It's still 0.000 something. It's just a little bigger than the ones next to it and the ones beyond it. So exactly anything is incredibly unlikely. If you flip the coin 40 times and got exactly 20 heads, I'd be a little surprised. If you flip a coin 2 million times and got 1,000,000 heads, I'd be incredibly surprised. So it's not about exactly anything. Like I said, it's about territory. So broadly speaking, if he flips the coin a lot of times, 40, we expect to get something in the vicinity of half heads, right? Broadly speaking, many, probably, close. You flip the coin many times, if it's a fair coin. If you flip it many times, you'll probably get close to half heads. So all you see that we're really doing is quibbling about many, probably, and close. Given this many, is 2048 close, or is it not so close? So let me recap that. You flip the coin 4,000 times and get 3,500 heads, and you're going to seriously doubt that it's a fair coin. You flip the coin 40 times and get 2017 heads, about half. Then you say, well, it's perfectly plausible that the coin is fair. So you see what we're doing is we're in the gray area, right? Is this more like 2020 or is it more like 3500? In context, is 2048 reasonably close to half? Or is it suspiciously far from half? Well, at a glance, you can't really tell, right? If you remember the various pictures that we had with the bells that were centered in the same place, but very thinner and thinner for bigger and bigger N, the gap between whatever proportion of heads this is, I didn't actually compute it there, so let me grab my calculator. 2048 divided by 4040 is not a nice number, but for verbal purposes, let's call it 0.5069. So 50.69% heads, 0.50693 something, so 0.5069-ish, 0.507. That's close to a half, yeah, sure, but broadly speaking, but you know, for 0.506, 0.507, well, it rounds to 51. You know, 51 heads wouldn't be unusual for 100 flips. 507 heads might be a little more unusual for 1,000 flips. 5069 out of 10,000, well, you know, who knows? So remember, those pictures that we had with the taller and thinner bells, that gap between center and wherever our tick mark is, becomes more and more significant, becomes harder and harder to get to for a large sample, right? We talked about this in the end of a couple of these sections, but I guess the best place to do it would be section 8 under the circumstances. I don't remember if I had a picture associated with this. I did. So, you know, less than 49% heads. Well, it's not that unusual for 100 flips, but it's incredibly unusual for 40,000 flips, right? The area on the small side of 49 gets smaller and smaller and smaller and finally is insignificant, right? So it's the same idea. If you flip a coin 100 times and get less than 49 heads, 49% heads, same thing, it's not that unusual. But if you flip it 40,000 times and get less than 49% heads, then that's incredibly unusual, right? So it's about the context. 2048 divided by 4040 is about 0.5069 something. You can't tell at a glance whether that's close to a half, right? It's about the context. For 400 flips, it may be relatively close to a half, but for 4 million flips, it's cosmically far away from a half. So you can't tell at a glance. You've got to run the numbers. So how weird is it to get 2048 heads out of 4040 tosses? Well, again, exactly anything is pretty negligible, particularly for large samples. So we've got to be a little bit more careful about what we mean. So let's formulate some alternatives. Let's be more specific about what we mean by an unusual coin or unusual results for a fair coin. Would it be unusual for a fair coin to do such a thing in the sense that maybe it will make us reconsider and decide that the coin is loaded to favor heads? So there will be the alternatives we'll set for ourselves. Either the coin is fair and he happened to get a lot of heads, or it's loaded to favor heads, and that's the reason the proportion of heads is as high as it is. Let me say that again. Either the coin is fair and he happened to get a high proportion of heads, or the reason he got such a high proportion of heads is because the coin was loaded to favor heads. It wasn't a fair coin. So there's the universe we inhabit. Either the coin is got a 0.5 chance of landing heads, that's our P, or else it's loaded to favor heads, in which case P, the probability of a head for this coin, is more than a half. Okay? So for the sake of argument, those are our alternatives. Now, of course, there is always that distant third possibility. There's no reason the coin, for the sake of argument, the coin could be loaded to favor tails. The probability of a head could be less than a half, and this could be even more unusual. Okay? Well, more on that a bit later, but the bottom line is we're not terribly interested in it at the moment. And however you slice it, getting 20-48 heads out of 40-40 tosses, being more than a half, doesn't make you think for a moment that the coin is loaded in favor of tails. Maybe it is, but it would never make you consider that possibility, right? So more on that a bit later, but for the sake of argument, those are our alternatives. Either it is a fair coin and he happened to get an unusually high proportion of heads, and maybe it's not that unusual, we'll see. Or the reason that he got such a high proportion of heads is because the coin is loaded to favor heads. So if the coin is fair, then the probability of a head is 0.5. And if the coin is not fair, specifically if the coin is loaded to favor heads, then the probability of a head, that is P, is greater than 0.5, right? Now, what's the difference between the coin being fair and the coin not? What is the difference between the coin being fair and the coin being loaded to favor heads? What is the difference between P being a half and P being greater than a half? Well, in the former case, you know the probability of a head for this coin. It's a half. In the latter case, you don't know the probability of a head for this coin. It's more than a half, but okay, what is it? Is it 0.51? Is it 0.7? Maybe it's 1. Maybe it's a two-headed coin. There's a lot of P's that are greater than a half, right? Maybe it's just slightly loaded in favor of heads, 0.51 probability of a head. Or maybe it comes up heads 3/4 of the time, 0.75. Or maybe it comes up heads all the time, P is 1. That is a two-headed coin. Oh, well, not in our case, obviously. But, we don't know as a general rule. So there is a big philosophical difference between the coin being fair and the coin being loaded in favor of heads. The coin being fair means we know what P is. The coin being loaded in favor of heads means that we don't know what P is, only that we've eliminated a lot of P's and we're left with the ones greater than a half. Plural, the ones. So you see, there is no good assuming the coin is loaded to favor heads for the purpose of running the numbers, because we literally do not know what that means. Remember, this is all based on a normal distribution. For a large sample, and 40-40 certainly qualifies, the proportion of heads that we're going to get, the statistic, p hat, the sample proportion, is approximately normally distributed, centered at P, with standard deviation square root of P times 1 minus P over N. That's right out of section 8. And N is certainly 40-40. You'll give me that. So the probability rules for what's likely to happen when you flip the coin 40-40 times are that it's approximately normally distributed, centered at P, with standard deviation square root of P times 1 minus P over 40-40. But if the coin is loaded in favor of heads, we don't know what P is, and we can't fill those blanks with numbers. On the other hand, if the coin is fair, then we can fill the blank with numbers, right? So if for the sake of argument, if it's a fair coin, or let's say we have a fair coin, then the probability rules for what's likely to happen on 40-40 flips, the proportion of heads is normally distributed, centered at P, which we're assuming to be 0.5, and likewise, standard deviation. So these are the probability rules. This is what the sample proportion of heads, These are its probability rules for a fair coin. For an unfair coin, we have no idea. We need to know we need more information than unfair in order to know P. So there's our question. If you want to know whether this is unusual, if you want to know whether 2048 out of 4040 heads is unusual, if you want to know whether that tick mark is close to the center or far away from the center, then you need to know what a fair coin flipped 4040 times was likely to do, right? So there's our question. We'll take our previous question and we'll make it more specific. What is the probability of a fair coin resulting in so many heads? What is the probability of a fair coin flipped 4040 times, giving you at least 2048 out of 4040 heads, giving you at least 0.50. For verbal purposes, I'll call it 0.5069, but as you can see here, I'm trying to eliminate any intermediate rounding. What is the probability of a fair coin flipped 4040 times, giving a proportion of heads at least as high as 0.5069-ish? Now remember, in our perfect normal model, exactly anything is negligible, so we can be pretty free and loose here with the greater than or the greater than or equal to. But strictly speaking, we're including the possibility of getting what we got, so at least. So we know how to play this out, right? This guy could be compared to this number, 0.5069 something, by subtracting this, dividing by this, and looking it up in the normal chart. And from there, you just do it. So let's do it somewhat piecemeal here, carefully. The square root of 0.5 times the other 0.5 divided by 4040. So the bottom is 0.0078664597. Now again, be very careful how you round. Your end game here is to accurately get z to two places after the decimal, right? So it would be a very bad idea to call this 0.008 or even 0.0079. We'll keep a fair amount of accuracy. If you've got an answer key button on your calculator, so much the better. Try not to do any intermediate rounding or, whatever you think you're going to need two places after the decimal. Keep 5 or 6 at all times, and then you've got a good shot at covering yourself. But bottom line is, I'm not going to do any intermediate rounding whatsoever. So I'm going to type in 2048 divided by 4040, which I already know, but then I won't have it rounded, minus 0.5, close parenthesis, divided by answer. Or, of course, you could do all in one big gulp with lots of parentheses, right? And what I get is 0.880.104.34857, which is more than I need, right? It is 0.88. So then for the purposes of looking it up, remember, greater than. So it's 0.88, which is too small to see. 0.88 would be the next one. 8106, but greater than, so 1 minus 8106. Well, here's some advice for the future. If, again, as with all shortcuts, be sure of your ground before you indulge shortcuts. Otherwise, that's how you get lost. But by now you've probably noticed the symmetry in these charts, right? Greater than 0.88, which is 1 minus this, is exactly the same as looking up negative 0.88 in the first place. So without a calculator, well, you have a calculator here, but for the sake of argument, 1 minus 8106 is going to be 1894. Don't believe me? I'll do it. 1 minus 0.8106, sure enough, 1894. More on that as we go, but the bottom line is our focus now is on, with confidence intervals, remember our focus is on the big middle territory, probably close. With hypothesis tests, our focus is on the small tail or tails, unlikely to be far apart. So our focus is on the tails. A single tail is always less than a half. Well, bottom line, the single tails are on this page of the chart. It's a shortcut. So if you're uncomfortable with it, then suffice to say that it is greater than 0.88, so it's 1 minus 8106. But ultimately, either way, it's 1894. So there's our answer. Call it for verbal purposes, call it 19%. What is the probability of a fair coin resulting in as high a proportion of heads as he got? Well, it would happen 19% of the time. That's almost a fifth. That's almost 1 time out of 5. So in other words, judgment call, it's just not that unusual. It is technically unusual in the sense that it's less than a half, right? But if you had a less than a half chance of dying tomorrow, you'd sit up and think, right? So if you had a 19% chance of dying tomorrow, it would be enough to make you sit up and think. So in the grand scheme of things, it's not what I would call unusually small, right? More on these judgment calls a bit later, but for the moment I'm just more, if you're already jumping ahead of me and wondering where's the cutoff point, we'll talk about that. But the bottom line is that happening 19% of the time through random chance is nobody's idea of hard to believe it could have just occurred. So in other words, judgment call, something that happens 19% of the time through random chance could very easily have just happened. Ergo, there's no particular reason a fair coin couldn't have done what we just saw it do. Therefore, there's no reason it couldn't be a fair coin. You see, it's about benefit of the doubt. It is plausible up to a point that the coin is fair, and we have not yet reached that point, because it wouldn't be that unusual for a fair coin to do what we just saw it do. In other words, it wouldn't be unacceptably unusual. It wouldn't make us rethink our premises. Okay, what I just saw would occur 19% of the time through random chance. That's not going to make me reconsider my premises. It is perfectly reasonable that it could have just occurred. A fair coin flipped 40 times. Well, 19% of the time you'd get as many heads as he got. 19% of possible samples of 40 would result in as many heads as he got. Judgment call, it's just not that unusual to get as many heads as he just got. It's still plausible that the coin is fair. We have no evidence that the coin is loaded in favor of heads. We have no evidence that the probability of a head for this coin is more than a half, so do not reject that theory. We will not reject the theory that the coin is fair. We find no evidence that the coin is loaded in favor of heads. More on this guilty, not guilty stuff in the next example. But that's the basic logic of what we're doing. I'll give you more of the jargon in the next example, but this is just to get your feet wet. Assuming the coin is fair, we run the numbers and conclude it wouldn't be that unusual for a fair coin to do what we just saw this coin do. Ergo, it is still plausible that the coin is fair. Now again, that's benefit of the doubt. There are all kinds of coins that could plausibly result in 2048 out of 40 heads, right? Maybe it comes up heads 51% of the time. It wouldn't be that unusual for that kind of coin either. So I'm not saying the coin is fair. I'm saying that it is one of the many theories that is still plausible. We're only testing this one. It is still plausible that the coin is fair. I'm not saying it is a fair coin. I'm saying I've got no reason to doubt the theory that it's a fair coin. There's a little picture of Eric Roberts from The Dark Knight on the Blackboard discussion boards. It's not about what's true, it's about what you can prove. Right? Well, prove is a very strong word in statistics, but nevertheless, to the extent we prove anything, we prove that the coin is loaded in favor of heads. We are just not rejecting the theory that it's fair. You see, the theory that the coin is fair is on trial. And like Eric Roberts, it's either guilty or not guilty. Either the sample convicts the theory that the coin is fair, or the sample fails to convict the theory that the coin is fair. This sample does not constitute evidence against the theory that the coin is fair. It does not constitute evidence that the coin is loaded in favor of heads. Anything might be true, but it's still plausible that the coin is fair. Not guilty. Okay? Second example, I'll give you a bit more of the jargon. Example 2, Cactus Fabric Softener claims that 60% of customers prefer their brand. A simple random sample of 2,000 customers, fabric softener buying people, whatever, reveal that 1140 prefer their brand. So our population in this case is all fabric softener buying customers, right? Simple random sample of 2,000 customers reveals that 1140 prefer their brand. Now, before I even run the numbers, it's important to note what the question is. Does this sample constitute evidence that they're exaggerating? So one of two things is the case. As far as this question is concerned, either they are telling the truth and 60% of customers prefer their brand, or they are exaggerating, in which case less than 60% of customers prefer their brand. And by the way, this is before I divide this out. So from the logic of the question, not from the numbers, not from the sample, not from the statistic, not from what we happen to get, from the logic of the question, either they are telling the truth and it is true that 60% of customers prefer their brand, or they are exaggerating and less than 60% of customers prefer their brand. Just like the coin was either fair or loaded in favor of heads, they are either the proportion of customers who prefer their brand is 0.6 or it's less than 0.6. So there's our P, the proportion of all customers who prefer their brand. They're claiming that P is 0.6. If they're exaggerating, then P is less than 0.6. So you see, it is the question being asked, not the numbers. It is the question being asked that sets out the alternatives. It is certainly possible that more than 60% of people prefer their brand, and they are just trying to claim it's 60 in order to cover themselves so they don't issue a false statement. But we're not interested. If we're a member of the fabric softener buying public, then the extent of our interest is whether we're being cheated, right? So this is the logical question to ask. Either they are telling the truth or they are exaggerating. That's the extent of our interest. But more to the point, it is the question we are asking. And the question we are asking sets up those alternatives. Either P is 0.6 or it's less than 0.6. Now, in point of fact, if you divide it out, 1140 divided by 2000 is 0.57. So it is less than 60%. But is it suspiciously less? We'll find out. So, some jargon for you. The null hypothesis, that's the theory being tested. That's the theory that is either plausible up to a point, or you go beyond that point and it's no longer plausible. The null hypothesis, H sub 0. The null hypothesis, H0, is a theory about what P equals, a potential value for the purpose of running the numbers. Again, the difference between the coin being fair and the coin being loaded in favor of heads was the difference between knowing P and not knowing P. Likewise, the difference between the fabric softener company telling the truth, in which case P is 0.6, and the fabric softener company exaggerating, in which case P is less than 0.6, is the difference between knowing P and not knowing P. If they're telling the truth, we know what P is, it's 0.6. If they're exaggerating, we do not know what P is, only that it's less than 0.6. There's a lot of different numbers that are less than 0.6. Maybe 59.99% of people prefer their brand, or 59%, or 58%, or nobody. Or, again, if it's truth you're after, we can now, if it is certainty that you're after, we now know two things. We know that somewhere in the world were 1140 people who like their brand, and somewhere in the world there were 860 people who don't like their brand. Beyond that, it's a crapshoot. Beyond that, it's all playing the odds. You always want to remember this with confidence intervals and hypothesis tests. You want to have that sarcasm in the back of your mind. It is entirely possible. It's unlikely, to be sure. It is highly unlikely, but it is entirely possible that we have just found the only 1140 people in the entire world who would ever buy their brand, in which case P is essentially 0. Or, at the other end of things, it's entirely possible that we have just found the only 860 people in the world who don't like their brand, in which case P is basically 1. So if it's certainty you're after, the proportion of people who prefer their brand is somewhere between none and all, 0 and 1. And we didn't need to run this sample to know that. So it always pays to be a little bit sarcastic about this, because it will help you to avoid leaping to conclusions that you maybe are not really allowed to leap to. You always want to bear in mind that although this sample resulted in 1140 out of 2000, the next sample might not. The next sample will give you something different. It's highly unlikely it'll give you exactly 1140 again. So how reliable is this? Well, how likely is the next sample to give you something similar? It's the same question. It all comes down to the sampling distribution of p hat. How much do samples of size 2000 bounce around, and what are they bouncing around? The sampling distribution, the stuff from section 8. So the null hypothesis is, in general, the null hypothesis is a specific theory about the parameter, singular. And the alternative hypothesis is a range of possible other things that can be going on. I want to state that in the broadest way possible to call in the later sections 21, 22. But that's the idea, is that the null hypothesis is singular. It is an explanation for what is going on in the population. The alternative hypothesis is plural. It is other possible explanations, sometimes every other, but in general, other possible explanations, plural. So the null hypothesis is singular. The alternative hypothesis is plural. For the foreseeable future, it means the null hypothesis always involves an equality, and the alternative hypothesis is an inequality, less than, greater than, not equal to. We'll worry about not equal to in the future. So in this particular section, and similarly in section 13, it means that the null hypothesis is that the parameter equals something, and that the alternative hypothesis is that the parameter, p in our case, is less than something, greater than something, not equal to something. So for instance, in this example, the null hypothesis, the theory that we're testing to see whether it's plausible, is that 60% of people prefer their brand. P is 0.6. And the thing that we'll go with, if that turns out to be hard to believe, by the process of elimination. Remember, there are only two alternatives here that we're interested in. They're telling the truth or they're exaggerating. So by the process of elimination, if it's hard to believe they're telling the truth, then you're led to the conclusion that they're exaggerating. So if it turns out to be hard to believe that 60% of people prefer their brand, then their exaggerating is what we're left with by the process of elimination. HA, P is less than 0.6. Less than 60% of people prefer their brand. If H0 is the truth, then the company is telling the truth. If HA is the truth, then they're exaggerating. And those are the only alternatives in play. Again, notice that if H0 is the truth, we know what P is, but if HA is the truth, we don't know what P is. Similarly, if we want to put the jargon back here in this question, then H0 would be P is 0.5, and HA would be P is more than 0.5, greater than 0.5, because, that's what it means for a coin to favor heads. It comes up heads more than half the time. P is greater than 0.5. So this was a greater than alternative, and this is a less than alternative. In our next example, we'll do a not equal to alternative. Now, before you can say that figuring out the alternative is not that big a deal, it kind of is. I mean, there are some books that'll give you trick questions. I'm not going to give you trick questions. For instance, getting 0.5069 heads provides absolutely no evidence that the coin is loaded in favor of tails, right? Is 0.5069 suspiciously more than a half? Well, if so, the coin is loaded in favor of heads. That turned out not to be the case, but it's a reasonable question to ask. Is 0.5069 suspiciously less than a half? No, of course not. It's not less than a half at all. Is 0.5069 suspiciously less than a half? No, it's not less than a half at all. So suspiciously doesn't enter into it. So in other words, do we have evidence that the coin is loaded to favor tails? Do we have evidence that the coin comes up heads less than half the time? That would be a silly question. It's a foregone conclusion. 2048 out of 4040 is not suspiciously less than a half. It's not less than, suspiciously, or otherwise. So there's no test to run, there's no numbers to run. Likewise, in our case, in point of fact, 1140 out of 2000 is 0.57. So 57% of the sample preferred their brand. If that's suspiciously less than 60, then they're exaggerating. If it's only luck of the draw less than 60 and it's not all that suspicious, then it's still plausible they're telling the truth. So that's our question. Is 57% suspiciously less than 60%? What's a fair question? We'll run the numbers. We'll find out. Is 57% suspiciously more than 60%? No, of course not. So a greater than alternative was never in play, just as the coin being loaded in favor of tails, less than 0.5, was never in play back here. I'm not going to ask you trick questions. So with that in mind, why do I belabor this point above when I say figure out the alternatives from the grammar of the question? Figure out H0 and HA, always from the grammar of the question, not from what the numbers happen to be. Why do I belabor that when it's brutally obvious what tail is in play here? Because we haven't talked about this yet. How many tails are in play is not obvious. If it is a single tail, then it's obvious which tail is in play. 57% is not suspiciously more than 0.6. 0.5069 something is not suspiciously less than a half. If we're talking about a single tail, then it's obvious which tail is the legitimate question and which tail is the stupid question. But it is not obvious that we're talking about a single tail, so this is all for the future. In other words, when you formulate HA, it's not so much a question of whether it's less than or greater than. That should be comparatively obvious. And by the way, if you get it backwards, it's easily fixed at the end just by changing a sign on your Z. But it's never, in the real world, it's never a question of whether it's a less than or greater than alternative. That should be comparatively obvious. To finish my thought, it's never a question of which tail. That should be comparatively obvious. It's a question of how many tails. So what is the key word here? Favor heads. Immediately tips you off you're talking about only one tail. This being 0.5069, it may be suspiciously to the right of 0.5, but it's not suspiciously to the left of 0.5. Likewise, exaggerating, if nothing else, should tip you off that you're talking about a single tail. Everything else you can cope with. Everything else you can correct for when you make mistakes in the signs and so forth. If you have the wrong tail, then it will have a way of working out when you run the numbers, if you know what you're doing. But if you have one tail instead of two, or vice versa, then that's going to be a little costly. So everything will take care of itself as long as you peg the keywords in the question that tell you whether you're talking about one direction or two. In favor of heads, favoring heads, one directional. Everything else will take care of itself, even if you make some mistakes in the short term. Exaggerating, one directional. Does the sample constitute evidence that they're underestimating? No, of course it does not. 57% is not suspiciously more than 60%. So, as long as you can find the words in the grammar of the question that tip you off that you're talking about one direction, or a lack of words that tell you that you're talking about two directions, more on that, then everything else will have a way of taking care of itself. The bottom line is that 57%, this 57% of the sample preferred their brand. That might constitute evidence that less than 60% of people prefer their brand. It certainly does not constitute evidence that more than 60% of people prefer their brand. It may be true that 60% of people prefer their brand. It may be true that these are the only 860 people in the universe that don't prefer their brand. Anything may be true. But again, it's not about what's true, it's about what you can prove. It's about what the sample allows you to conclude. 57% of the sample preferred their brand. That may be suspiciously less than 60%. It may be suspiciously far away from 60%. We'll talk about that in the next example. But it's not suspiciously more than 60%. So a greater than alternative was never in play. Again, this may be suspiciously more than half heads. It may be suspiciously off target from half heads, in which case the coin is simply not fair. P is not equal to a half. But it is not suspiciously less than half heads. The coin favoring tails was never in play. Maybe the coin does favor tails, but this sample does not allow us to conclude such a thing. Okay, so we've got our alternatives set up here. Either they're telling the truth and 60% of people prefer their brand, or they're exaggerating and less than 60% of people prefer their brand. Now again, we know that a sample of size 2000 is normally distributed, centered at P, whatever that is, with standard deviation square root of P times 1 minus P over 2000. So H0 being the case allows you to fill the blanks. Put a 0.6 in where you have a P. HA being the case does not allow you to fill the blanks. You can't type less than 0.6 into your calculator. It just doesn't work. HA means you know what H0 means you know what P is. HA means you do not know what P is. It is no good assuming the company is exaggerating because we do not know what that means. It's not specific enough to run the numbers. 59% of customers prefer their brand, run the numbers one way. 58% of customers prefer their brand, run the numbers another way. 59.99% of customers prefer their brand, run the numbers a third way. We don't know. You have to assume an equality for the purpose of running the numbers. What this means is that H0 is plausible up to a point. And if we pass that point, then HA is what is left by the process of elimination. We either do or don't reject H0. We either do or don't find evidence of HA. That is always the way I will word things in so many words. Do we or don't we reject something? You're talking about H0. Do we or don't we find evidence of something? We're talking about HA. That's important because questions can be worded in different ways and people can make all kinds of claims. They can claim the truth is 60%, they can claim it's less than 60%, but however things are worded, there's always a number in play and there's always a range as an alternative to that being the case. And the equality is always the H0 and the inequality is always the HA. H0 is plausible, to recap, H0 is plausible up to a point, but if the sample makes it hard to believe, we pass that point. You either reject it or you don't. HA is what you're left with by the process of elimination if you reject H0, so you either find evidence of it or you do not. H0, benefit of the doubt. HA, burden of proof. Say it again. H0, benefit of the doubt. HA, burden of proof. Okay, why am I giving the Cactus Fabric Softener Company telling the truth the benefit of the doubt? Because of math. Not because I trust this company, not because I want to give them the benefit of the doubt. They are making an equal claim, and equal claims get the benefit of the doubt. If they claim that more than 60% of people prefer their brand, that's an HA kind of thing. So the math forces me. The equality gets the benefit of the doubt. The fact that it's the Cactus Fabric Softener Company claiming it is neither here nor there. So the Cactus Fabric Softener Company making this particular claim happens to get the benefit of the doubt, but it is the equality version of the facts that gets the benefit of the doubt. That's a little bit more clear-cut up here. There's no particular reason why I should give the Cactus Fabric Softener Company the benefit of the doubt in the real world. It's just a consequence of the math. But up here, of course, you're going to assume the coin is fair until the evidence says otherwise, right? The coin being fair logically has the benefit of the doubt. Again, that is neither here nor there. It is the fact that you know P for a fair coin and you don't know P for a coin that favors heads. It's the math which tells you which one gets the benefit of the doubt, which tells you which one is H0 and which one is HA. The fact that you would probably assume a coin was fair until the evidence became overwhelming is irrelevant. It's the math that tells you which one is H0 and which one is HA. Okay? So we'll run the numbers. We always assume H0, the null hypothesis. For the moment, the equality version of the facts, for the purpose of running the numbers. In the end, it's either plausible in light of the sample, do not reject the theory, no evidence of the alternative, or it's not plausible in light of the sample, do reject the theory, evidence of the alternative. If the theory being true, all of the calculation is run on H0 being the case, and the number that results at the end has no life outside of the assumption that H0 is the case. The bottom line is that we compute that probability and we do not believe in unlikely things. So if H0 being true results in a very low probability, we do not believe in unlikely things. We reconsider H0, but not until then. In other words, the smaller the H0, the smaller the probability at the end is, the harder H0 is to believe. You never want to think of the number at the end, the probability, for instance, the 1894. You never want to think of this as the probability of the coin being fair. That makes absolutely no sense. There is no probability of the coin being fair. The coin is either fair or it is not. It is a parameter. It is a fact about the universe. Probability, randomness, means you can repeat and get a different answer. There is no probability of the coin being fair. It simply is or isn't. What had a probability was what is likely going to happen when you flip a coin 40 times. Again, it's the backwardness that makes it hard for people to think about. Now, the question you're asking yourself is always in general terms exactly the same. Assuming H0 is the case, assuming that is the truth of the universe, what is the probability of getting a sample as extreme as ours? So let me go back a bit. If the theory being true makes the sample very unlikely, then we'll reject the theory. H0 is the foundation of the calculation. If it produces something very unlikely, the foundation crumbles. Again, H0 is the basis of the entire calculation. If assuming the coin is fair leads you to the conclusion that something very unlikely has just happened, then reconsider the theory that the coin is fair. Low probability. Or, as in the case above, if assuming the coin is fair does not lead you to the conclusion that something weirdly unlikely has happened, then it is still plausible that the coin is fair. Now we'll talk about the cutoff points, but 19% of the time is just not that unusual. So the question in general terms is always the same. Take the time to set up H0 and HA in abstract terms, because by the time you get to the end of the problem and have the number, you're not going to remember what any of this means. If you've got the H0 and the HA to refer to in abstract terms here, then it is easily recovered, right? H0 being the case means that they were telling the truth. HA being the case means they were exaggerating. You don't have to think about that if you've got the H0 and the HA to look at. So just plan for the future. You're going to lose your place, but you're going to lose your assumptions by the end. You're going to be doing the math, and you're going to forget what you were talking about. So have them to refer to. The question in general terms is always the same. Assuming H0, what is the probability of a sample as extreme as ours? Well, what does extreme mean in context? If the alternative is P being greater than a half, then extreme means a weirdly high number of heads. Right tail, way over here. It is high proportion of heads that incline you toward the possibility that the coin might be loaded in favor of heads. Not so, here's the center. So if it's not all that high, then it's still plausible that the coin is fair. But if it's weirdly high, then we're going to go with the theory that the coin is loaded in favor of heads, right? It is high proportions of heads that incline you to the coin being loaded in favor of heads. Likewise, it is low proportions of people in the sample liking their brand, which make you think they're exaggerating, right? So the arrow is your tip-off, right? P is greater than a half, you're talking about being over here. P is less than 0.6, you're talking about being over here. So in general terms, the question is always the same. What is the probability of a sample as extreme as ours? Assuming the coin is fair, what's the probability of a sample as extreme as this? Well, what do we mean by as extreme as? We mean as high as. In this context, assuming the company is telling the truth, what is the probability of getting something as low as 57%? So it's over here. It's the left tail. It's the low territory which you're interested in. For a coin which might be loaded in favor of heads, as extreme as translates a high proportion of heads incline you toward the coin being loaded in favor of heads. For a fabric softener company which might be exaggerating, low proportions of customers liking their brand incline you to conclude that they're exaggerating. So the bottom line is, if this was a greater than 0.5, then you're talking about these are the samples over here, the right tail. Those are the ones which count against H0, which incline you toward HA. On the other hand, if it's like you see it, less than 0.6, then samples over here, suspiciously less than 0.6, left tail, those are the ones that incline you toward HA, that make H0 harder to believe. So you've got to translate as extreme as in context. It's a two-step process. From the grammar of the question, not the numbers, I mean not the sample numbers, from the grammar of the question you get the alternative. And then from the alternative, less than, greater than, not equal to, you interpret what you mean by as extreme as. Left tail, right tail. In the next example, both tails. So in our case, low p-hats over here, left tail, constitute evidence of HA. In the previous sample, high proportions did, because those were our alternatives. So now that we've got our question, we can do the Section 8 problem that results. Again, the prologue is all grammar and logic. The math is exactly what we did in Section 8. Assuming that P is 0.6, what's the probability of a sample as low as ours? Low. Left tail. So, assuming 60% of people prefer their brand, is it suspiciously weird to get something as low as 57%? Left tail. Well, we run the numbers, right? We know that P hat is bouncing around P, which we are under the umbrella of assumption H0. While we are under the umbrella of assumption H0, P is 0.6. So we'll subtract P, which given the highlight is 0.6, and we'll divide by square root of P times 1 minus P over 2,000, which given the highlight is the 0.6 in the blank. Run the numbers, and you get negative 274. The corresponding tail, 0, 1, 2, 3, 4. This one, I think. 4. Column. Negative 274. 0031. Notice, by the way, that hypothesis testing is about the only time that close enough is good enough. At the end of the day, the question is just whether it's suspiciously low. Being 1 or 2 entries off here is not the end of the world, but it is 0031. So there is the answer to that question. Assuming that 60% of people prefer their brand, what's the probability of picking 2,000 and getting something as low as we did? 0031. That is to say, it would happen on 3 out of 1,000 samples, 31 out of 10,000 samples. It's pretty weird. That is pretty unusual, right? If there's a 19% chance of, if 19%, 18%, what is that, about a fifth, right? If there's about a 1 in 5 chance of something happening, it's not that unusual. But if it happens 3 times out of 1,000 or 31 times out of 10,000, this is not even a third of 1%. That's pretty unusual. So again, we'll talk about the cutoff point a bit later, but it is certainly a very, very different place than 1894, right? So just as this was pretty clear-cut in the not that unusual territory, this is pretty clear-cut in the is pretty unusual territory. If they're telling the truth, if 60% of people prefer their brand, this sample is very unusual. You'd get something this low 31 times out of 10,000. If they're telling the truth, this sample was very unlucky for them. Unbelievably unlucky. Suspiciously unlucky. Is 57% suspiciously less than 60%? Well, yes, in context. So H0 is literally suspect. H0 is the basis of, remember, in the end it's not that complicated. You have a theory. If the sample makes it hard to believe, don't. You have a theory. If the theory being true would make the sample you just got suspiciously unusual, then reject the theory, right? I'll say it again. You have a theory. If the sample makes it hard to believe, don't. You have a theory. If the theory being true would make the sample you just saw suspiciously unusual, low, high, whatever, then you'll reject that theory. So yes, H0 is no longer plausible. We will reject H0, and by the process of elimination, we have evidence of HA. If 60% of customers prefer their brand, it would be very unusual for a sample to result in something this low. Now, of course, weird things happen in life. So at the end of the day, it is a judgment call. You are making the most plausible alternative in light of the sample you have. You're running the numbers, you're getting the probability. Sometimes unlikely things happen, but you can't assume they just did. So at the end of the day, it is going in the most plausible direction Reject H0, don't reject H0. Evidence of HA, don't find evidence of HA. You're simply going in the most plausible direction given the number that you have at the end. Yes, it's guesswork, but it's intelligent guesswork. The most plausible explanation of the facts is that they are exaggerating. It is no longer plausible that they're telling the truth. Now, if that confuses you, remember as a mnemonic device that this plays out pretty much the same way. Is the number at the end suspiciously small? Do we reject H0? Do we find evidence of HA? Yes, yes, yes. No, no, no. Is the number at the end suspiciously small? No. Do we reject the theory that the coin is fair? No. Do we find evidence that the coin is loaded in favor of heads? No. Is the number at the end suspiciously small? Yes. Do we reject the theory that they're telling the truth? Yes. Do we find evidence that they're exaggerating? Yes. So, yes, 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 no, no, no. The probability of getting a sample as extreme as ours, as high in the first problem, as low in the second problem, as different in the problem to come, the probability of getting a sample as extreme as ours on the current understanding of the facts, H0, is called the p-value. Do not think of it as the probability of H0 being true. H0 is either true or not. It is true that the smaller the p-value is, the harder H0 is to believe. But don't think of it as the probability of H0 being true, because there is no such thing. H0 is either true or not. There's nothing random about it. There's no probability involved. What was probable was the sample we just got. And to have any perspective on that, you've got to assume you know what's going on in the world. So you assume H0 for the purpose of running the numbers. If it means that the sample you just got was very unlikely, then you rethink H0, but not until then. If the p-value is very low, reject H0. It is no longer plausible in light of the sample, and find evidence of HA. Is the p-value very low? Do we reject H0? Do we find evidence of HA? Yes, yes, yes. If the p-value is not that low, do not reject H0. It is still plausible in light of the sample, and do not find evidence of HA. Is the p-value low? No. Do we reject H0? No. Do we find evidence of HA? No. At no point do we use the word accept. Nothing is accepted. H0 doesn't have to be accepted. It's already got the benefit of the doubt until we reach the breaking point. We didn't for the coin, we did for the fabric softener company. Nor does it make sense to accept HA because it's not specific enough to be accepted, right? Yeah, you're not really figuring out what P is. You're only eliminating half the possibilities. So, or in some cases, you're just eliminating one possibility. If the company is exaggerating, we still don't know what proportion of people prefer their brand, only that it's less than 60%. If the coin is loaded in favor of heads, we still don't know the probability of a head for that coin, only that it's more than a half. It's not specific enough to be accepted. Nothing is ever accepted. Like a court of law, H0 is either guilty from a low p-value or not guilty from a p-value not that low. The sample either convicts it or fails to convict it. HA only comes into it, if it does, by the process of elimination. In light of the sample we have to work with, H0 is either plausible, do not reject, or implausible, reject. We either have evidence of the alternative or we don't have evidence of it. If you like sing-songy mnemonic devices, if the P is low, the null must go. The bottom line is we do not believe in unlikely things, and H0 is the basis of the calculation. So it is not believable if it being true means something just unlikely has occurred. Okay? It's not that complicated if you boil it down. You have a theory. If the sample makes it hard to believe, don't. You have a theory. If the sample makes it hard to believe, don't. My theory at the moment is that this video is 1 hour and 19 minutes, so I think I'm going to do example 3 in a separate video because we want to be a little bit more specific. All that really remains is, number 1, to do a not equal to example. They're a little tricky. And number 2, to talk about a specific cutoff point for what is too unlikely to believe. So we'll do that next time. Now, bear in mind, any question which starts off, what is too unlikely to believe, is the kind of answer that only a human being can answer, right? It's not a mathematical question, it's a judgment call question. But we can at least be intelligent about it, and we'll talk about that in the next second half of the Section 11 video.